Those of you who may not know, we are Dynamism. We're a professional seller of 3D printing solutions. Our big thing is that we are brand agnostic. So no matter what you're trying to do, we're going to be able to recommend the best 3D printing technology, the best materials and stuff like that. As you all may know, there's lots of different 3D printing processes and technologies. So we're kind of here to assist you in selecting the best hardware and materials. And as a reminder, so this is metal 3D printing for functional prototyping and short run production. Today, I'm going to be joined by Ethan. He is an application engineer from Desktop Metal, and he actually happens to also be on the marketing team, so it works out pretty well. Throughout the course of this, if you guys have any questions, we have a couple product specialists and application engineers ready to go. So go ahead and drop those questions in the chat, and we will get to them as they come in. All right, and I'm going to go ahead and hand it off to you, Ethan.
Great, thank you. Thank you for joining me, everyone. It's great to be working with Dynamism on this for our presentation today. So like Eric said, today we're gonna be talking about rapid prototyping and low volume production with metal 3D printing. Just a couple logistics, like Eric said, feel free to be using the Q&A throughout the webinar or the chat, I guess. Feel free to be chatting in your questions. We have tons of application engineers on the line who are happy to answer any of your questions, and I'm happy to take any questions at the end as well if I think there's anything that the entire group should know. Also, if you do have the option in Zoom for that side-by-side mode, I have quite a few metal parts with me here today that I'll be showing off throughout the webinar. So if you could view both the slides as well as the camera, generally that's the best way to view the webinar. Let's go ahead and get started. So quick agenda, we'll talk briefly about the promise of metal 3D printing and how it's adding value to different industries. We'll look at additive manufacturing based on metal injection molding, which is the process that the Desktop Metal products use. We'll look at a bunch of application examples. We'll look at some case studies and look at some real Desktop Metal customers and how they're adding value with the Desktop Metal printers. So quickly, the promise of metal 3D printing. If you're familiar with plastic 3D printing, a lot of these are going to be familiar, but they're a little bit unique to metal. We're going to be talking a lot today about rapid prototyping, so I won't go too much in on that point here, but just this idea of not just rapidly prototyping for form and fit like with plastic, but now we can actually functionally test our parts. We can put them into a high loading environment, high heat, corrosion environments, and actually see how our part's performing. You know, part consolidation, since we're now using an additive method, it's very possible to combine assemblies into one component. You know, complex geometries. And I like to clarify this point a little bit as well, because, you know, people have been doing complex geometries for a long time, but now we're able to do justifiable complex geometries. You know, we can print a part that's far more complex than what we could, you know, justify with a traditional manufacturing method, because the part cost is going to be quite a bit lower. The lead time is going to be quite a bit lower. So now we can justify those complex geometries that we wish we could do, but we just couldn't justify with traditional manufacturing. Design customization. Of course, since there's no tooling involved in the process, at any point in time, I can make slight tweaks to my model, upload it to the printer, and in a couple of days, I'm ready to send it out. Rapid tooling. Tooling is some of the most expensive and longest lead time components to create. So people are seeing a lot of value with actually printing their tooling, you know, printing their extrusion dies, your sheet metal tooling, your injection mold cores, you know, a lot of value added by printing those parts, you know, with metal 3D printing. On-demand manufacturing, where, you know, since the lead time is so low and there's no tooling involved, rather than having to warehouse all these components, now I can simply pull a file and just, you know, send it to the printer. You know, and in a couple of days, I'm ready to ship it out to the customer. And that kind of goes hand in hand with this idea of re-engineering of the supply chain. You know, as more and more printers are being deployed around the world, we're starting to see people send digital files rather than hard goods. So, you know, if a part's designed in the US and maybe they need it in the office over in Europe, you know, rather than, you know, machining that part, you know, or finding a machine shop over there that can do it, I can simply just send them the file. They have the same printer, the same system, and they can just upload it and have it in their hands in a few days. Like I mentioned, you know, today we're going to be talking a lot about rapid prototyping. And, you know, with Desktop Metal, especially with the metal prototyping, we like to talk about functional prototyping, which, just to reiterate, it's not just form and fit. It's not just, oh, does my bracket fit into my machine? Now we're talking about, how does my part actually perform under operating conditions? You know, high heat, high corrosion environments, you know, high loading environments, where we're going to need a metal part to withstand, you know, the actual operating environments. And now we can test, like I've said already, not just form and fit, but the actual function of the component. So let's talk a little bit about Desktop Metal before we jump into the products. Desktop Metal was founded in 2015 with the goal to make 3D printing accessible for engineers and manufacturers. And what I want you to take away from this mission statement is this idea of accessibility. You know, metal 3D printing has existed for a while, but Desktop Metal came out with the idea of trying to make it accessible. Accessible for the everyday engineer, the everyday manufacturer, not just these very, very high-end, manufacturers that can afford these laser-based systems, but now it's accessible for everyone, adding value to everyday engineers and manufacturers. We've been shipping for a few years now. We have customers all over the globe. We're shipping in 49 different countries. We're shipping some of the largest companies in the world as well as some of the smaller manufacturers, companies that are just getting started with metal 3D printing, or even with just getting started with 3D printing in general. It's not uncommon to see corporations that have a few, plastic printers, and then they have a Desktop Metal studio system, because it's so accessible. It's making metal 3D printing so possible for everyday engineers, everyday manufacturers to actually embrace this technology. The product line today, we have 4 printers. On the far left, you see our composite printer that actually prints carbon fiber, fiberglass, PEEK and PEC, very high-end thermoplastics. We won't be talking too much about that product today, but we have there's whole other webinars dedicated to that if you're interested in learning more about the composite side of Desktop Metal. There's the studio system, which we'll be talking a lot about today. That's the printer that I have behind me here in the studio. That's our office-friendly printer, great for metal prototypes, one-off parts, low-volume production, jigs and fixtures, tooling. It's an excellent machine for that because it's our most accessible metal printer, very easy to use, very, very accessible. Then we have the shop system, which we'll also briefly talk about today. That's really when you want to up your, your throughput. If you want to go from maybe 10 parts a week to hundreds or thousands of parts per week, the shop system is going to allow you to do that. It is a binder jetting machine. And then we have the production system, which is, our fastest metal 3D printer, another binder jetting machine that is really targeted towards, the factory floor for very, very, very high volume parts and very, very, very high throughput. But like I mentioned, today we're going to be focusing on the studio system and the shop system. So let me first talk a little bit about Powder Bed Fusion. So when Desktop Metal was founded, we generally saw that Powder Bed Fusion was too expensive and too slow for broad adoption. Generally the machines we were looking at were spending about $1 million in capital expenditures to produce about 1 metric ton of parts per year. And while this is a great technology, it's being utilized by lots of different corporations. It was mostly being utilized by the very, very high-end manufacturers, aerospace and medical device, for example, who really, really needed this very, very, very high quality, very expensive part and could actually justify the machine and part costs. On top of that, the materials were not overly familiar. There's no 4140, there's not a lot of tool steel options, there's no 6061 aluminum. In terms of, costs, the facility infrastructures are quite expensive. You have to have these explosion-proof rooms, quite labor-intensive post-processing processes. The part costs were relatively high, not a lot of automation, and then again, it's quite slow. So, while Powder Bed Fusion does produce, excellent parts, it can be very hard to justify this technology. So we looked at Powder Bed Fusion and we thought, wouldn't it be nice if we still had this on-demand appeal that you get from Powder Bed Fusion? You didn't need these special facilities or operators, and we had this broad palette of familiar materials. So, we kind of took that challenge of how do we make metal 3D printing accessible to the everyday engineer? And that's how we kind of developed our first product, which is behind me, the studio system. Before I get too in detail about how the studio system works, I first need to cover metal injection molding. So our printers are built around the chemistry and supply chain of metal injection molding. Metal injection molding is a powdered metal process. It enables you to create these very complex shapes and then mass produce them utilizing these inexpensive metal powders. It has widely validated and accepted standards, ASTM and ISO standards. It's used in a broad range of industries, everything from firespace, firearms, to consumer, to medical device. You can create a wide variety of different shapes in a wide variety of different alloys. So briefly about how metal injection molding works is you start with this low-cost metal powder and you mix it with a binder, which is similar to a glue. You then are going to create a feedstock and you inject that feedstock into a mold, very similarly to what you would do in a plastic injection molding process. What's ejected from the mold is your general part shape, and it's just being held together with that binder. Your metal powder is still just particles next to each other. That's all being held together with that binder. In the debinding step, you're going to remove most of the binder out of your part, leaving behind just enough to hold your part together rigidly, and then you're going to put it into the furnace. The furnace is going to get just below the melting temperature of the material, and then you're actually going to sinter your component into a strong, dense metal part. So this is a great technology. It allows you to mass produce parts utilizing these inexpensive powders. But the issue with this technology is the molding step. It requires this, massive injection molding press. You have to have these steel molds for each different part you want to make. So, if I want to make this gear today and I want to make, this clamp here tomorrow, I'm going to need a completely different tool that could take weeks to produce, as well as thousands of dollars to produce those tools. So this technology is really only utilized for very, very, very high volume production. So I commonly like to say that our products almost stand on the shoulders of metal injection molding because it's a very similar process, but of course we remove this tooling step. And that's how I'm going to introduce to you the studio system. So it's similar in that, we have a debinder, which you're seeing on the right, we have a furnace, which you're seeing on the left, but rather than having that molding step, we have a printer. So very similar. We're going to create a feedstock. I have a rod with me here today, actually. This is that combination of metal powder and binder, but the entire rod is encased in a wax. This makes it very, very safe. There's no loose powder at any point during the process. There's no powder handling. This is obviously very safe. I have it with me here in the office. These just come in, these cartridges that you slide in and out of the printer. Making it very, targeting accessibility. Rather than having to mold this material, we're just going to print it, layer by layer, similar to an FDM style print process. So this means, if I want to print one part today, when it's done, before I leave to go home for dinner, I can start a new part that'll be ready in the morning. I'm not tied down to any tooling. We have a similar debind step. It's going to remove about 80% of the binder in our process. And then we go into the furnace. We're going to sinter that part into a strong, dense metal part, like you see, I'll show a ton of examples today. I have a high detail scope here as well, but you're ending up with a strong, dense metal part. Just a quick look at the 3 distinct pieces of equipment. You have your printer. It's similar to the safest and most widely used 3D printing process of FDM. That means you have relatively familiar design guidelines, office safe materials. There's no powder handling at any point during the process because all the material is in these rods that are very safe to handle. And those rods are fully encapsulated, in these cartridges that you just slide in and out of the printer. Debinder, again, targeting accessibility. It's got this low emission design, automatic fluid distillation and recycling, safe for your office environment. The parts go into the debinder dry, they come out of the debinder dry, so you're never exposed to any debind fluid throughout any point in the process. The furnace, it's really, the first office-friendly sintering furnace. It fits through the office doorway. It's very easy to install. It has a peak temperature of 1400 degrees Celsius, which allows you to sinter, a wide variety of alloys to the highest material properties possible. So what's the result of this? We're getting like what we call a near net shaped part. It has resolution, accuracy, and surface finish that's quite similar to casting. Dimensional capability is about plus or minus 0.8%. But it's important to know, these parts are fully compatible with traditional finishing operations. For example, on this gear, I simply printed this gear in 17.4 stainless steel, debound it, sintered it, but afterwards, I needed a tighter tolerance on that inner diameter. So all I had to do, throw it on the lathe, machine down just a millimeter of that inner diameter, and now I'm hitting that tolerance that I needed. The parts are fully functional out of the furnace, but it's important to know, it's so much easier for me to machine that last millimeter on this part than have to machine this entire part out of a wrought 17.4 stainless steel, which would be very difficult and very expensive. Similarly, parts are fully compatible with traditional finishing operations like tumbling or media blasting. This part has been tumbled in abrasive media to give it that nice shiny finish that was needed for the application. Looking at materials, currently the system is printing 17.4 stainless steel, 316L stainless steel, H13 tool steel, and 4140 low alloy steel. Coming soon is going to be copper, as well as alloy 625, which is also known as Inconel. So giving engineers that wide variety of materials that most people are already familiar with working with, so that way, you're ready to get up and running as soon as you get a system. Material properties are meeting or exceeding, MPIF MIM standards. So you're getting material properties that are quite predictable, as well as quite familiar in terms of the powdered metal landscape that are allowing engineers to really make good use of these parts. So just a quick recap on the studio system. Really targeting accessibility. No hazardous powders at any point during the process. You're not required to wear any respirators throughout the process. There's no dangerous lasers involved throughout the process. You don't need any third-party equipment. You don't need any dedicated operators. You know, we could train anyone on this call to learn how to start printing your first part in, you know, in just 10, 15 minutes. It's almost as simple as just uploading your CAD file and sending it to the printer. There's no welded supports. I didn't talk too much about this today, but you know, in a powder bed fusion process, of course, your supports are welded straight to your part. In our process, we actually have a release layer. So you can see on this part here, you know, there would be a release layer all throughout the support here that allows me, you know, after sintering to just pick up my part right off the supports, saving lots of time and cost when it comes to post-processing. Which is a pretty cool technology. And again, no special facilities, very easy to get this up and installed in your office environment. So let's jump into some applications and look at how the studio system is adding value across a variety of different industries. So rapid prototyping. This is a worm gear speed reducer. You can see, you know, I have the worm gear here with me today, as well as this front flange. This front flange is going to eventually be a cast component, but before we go to the foundry, we scale up, we place a large order for these parts to be cast, we're going to want to test this part. We're going to want to test it under high loading, you know, with different motor sizes to ensure that this part's going to function before we place this large order. Same with these, you know, with these worm gear shafts. You know, maybe we want to try different thread profiles. We want to try different diameters. We want to try different keyway sizes. You know, then we want to actually test this part under high loading. You know, with metal 3D printing, we can functionally test this part very, very, very easily. You know, this part can be printed for just $86. You know, I could put a couple different designs on the print bed over the weekend and they're ready to test, you know, the next week. You know, this allows me to be able to very, very, very quickly prototype, but now in metal, to really try these different designs, these different thread profiles to ensure that when I move to a higher volume casting method, you know, we're getting the design we want. This crankshaft gear assembly. So this part is actually used to attach the crankshaft to the water pump as well as the oil pump. And this is a good example of some assembly consolidation. You know, originally this part was produced in 2 different separate gears. It was then welded together. But now, since we're 3D printing, you know, we can combine this into just one component and print it all together. You can see some of those overhangs are being self-supported, allowing this part to be easily prototyped, you know, with the studio system. And then on this part, actually, you know, we're looking to move to mass production on something like the shop system or, you know, even the production system where now we can produce this, you know, more optimized geometry in high volumes. The BMW water wheel. Oh, one thing I should note, we will be distributing the slides, of course, as well as a recording. So I have tons of parts I'm going to be going through today. So I will be moving a little bit quick, but you know, don't feel like you need to take screenshots or anything because we'll be distributing slides after this. This is a great example of, you know, a very complex part. This part was originally produced via Powder Bed Fusion for about $100, but it was far too expensive really to incorporate into any vehicles besides their very high-end racing vehicles. On the studio system, they're able to tweak the design a little bit to make sure they're having the exact design for the water wheel that they want, and then they can move to mass production on the shop system or the production system where they can get that cost down to just about $5 per part to really allow, you know, this part to be installed on many more vehicles than just on their very, very, very high-end racing vehicles. A valve body, you know, another part, you know, a lot of these parts eventually are going to be cast, but before we move to that casting method, we want to be able to iterate on these parts. We want to be able to test them. You know, this is actually a valve made out of Inconel, so it's made for those corrosive environments, actually in an oil and gas environment. But, you know, before we move to casting this part in high volume, we're going to want to be able to test it. We're going to want to be able to test it with the actual fluids that are going to be running through it, which means we're going to need to use metal. So with printing, you know, it's very easy for me to print one of these overnight, ready for testing the next week. So, you know, another great example of just how you can use, you know, the studio system to prototype these parts that eventually are going to be cast. You know, another example, this is another oil and gas component, but this downhole tool slip. I should have one here with me. Yep. You know, this part's actually used for a frictional hold between, you know, the frac plug, which is what you're looking at in the middle, and then a pre-existing drilled pipe to hold this stuff in place. You know, they're iterating on these designs of, you know, the actual geometry as well as, you know, some of these patterns. And you can see, you know, this is something that's still very much in development. You can see, you know, they have a couple different patterns on different designs because they're trying to still iterate and figure out what the best design is to use for this process. So another great example is how they can move very, very quickly because now they can try many different designs very quickly to understand, what is the one that we then want to move to mass production with, and we want to place an order, in thousands or tens of thousands. But, before we do that, let's produce a bunch of these with different designs to ensure that we're optimizing our design under high loading and these high heat environments that they're going to be seeing in the pump. John Zink is one of our customers in Tulsa, Oklahoma. They have a great prototyping story. So they are a leading vendor of emissions control and clean air combustion systems. And as emission standards are becoming increasingly stringent, they're having to get more and more creative in ways to, eliminate these emissions from the environment. So what are they mostly using the studio system for? They're doing lots of jigs, fixtures, custom tools, and dies. They're also, producing lots of these urgent aftermarket orders that would require parts far sooner than they could receive them from their casting suppliers. They're prototyping parts for testing purposes. And then they're actually doing quite a few designs that are just parts that just couldn't be made via traditional manufacturing, like this atomizer that I'm going to talk about in just a minute here. So one of their parts, one of the projects that they were working on was to improve the performance of this UHT atomizer for this LNG tanker. So this is an LNG tanker, it's a liquid natural gas tanker. And the problem was that the baseline atomizer that you're seeing on screen here was getting a very poor burner turn down during low load. So what does that actually mean? It means that when the ship was going slowly, it was getting very poor fuel efficiency. So John Zink was tasked with, how do we increase this fuel efficiency on the ship? We want to burn less fuel and, create less emissions and save money at the same time. John Zink very quickly understood that by altering the mixing of the steam and the fuel, they were going to be able to change the performance of the engine. So you can see they very quickly went through multiple different iterations of this atomizer. You can see the different profiles they tried, as well as some of the different curvatures. And then we're able to test all of these in metal to see how they actually performed. This is a burner component. There is lots of, fire and fuel being sprayed here. So they needed the metal here to, actually functionally test these components. You can see a couple more iterations and the journey to the final design that I have with me here today. I'll switch back over to my overhead camera, but the final part, was a huge success. They ended up printing this part in 316L, and they were able to radically improve the mixing of the fuel. So they went from a burner turn down of 15:1 to 25:1, which was about a 70% improvement, which ended up being a customer fuel savings of $90,000 to $160,000 annually. So, this one part was able to make a huge difference in terms of the mixing of the steam and the fuel to allow for that higher performance. This part actually features quite complex channels underneath here that are actually snaking through the part up to these teardrop shaped holes here. This is the part that can only be produced via additive manufacturing because it would be impossible to machine or get in and produce any of those holes inside of there. So a great example of, a way that, to do some functional prototyping on parts that are actually going to be printed and then actually producing the parts, end use. A quick look here, at the part actually firing. Very, very, very cool part. Lots of fire and explosions, as I said. So of course, metal was a necessity. Design studies. For example, on impellers, lots of different impeller types. But if you want to try, different shapes, different sizes, different numbers of vanes, it's very beneficial to be able to very quickly print different iterations. These parts would be very expensive to machine, and then we can actually, test out our component to see how does it perform, under high pressures in the pumping environments that the impeller is actually going to live in. You can see a couple different iterations here. Impellers are always a great thing to print. These vanes are very complex and would be very, very expensive to machine, because of some of the chattering that would be involved. And you can see, of course, these parts are very, very easy for us just to simply print. A hydraulic pump housing. Depending on the pumping components inside, these outside cast housings are going to change. They're going to fluctuate in size, they're going to fluctuate in dimension, different hole patterns to allow for these different, pumping components. So again, before we move to this high volume, casting process, we want to be able to test these different geometries, test how they are. It's so easy to make these changes in the CAD environment. How do we make it easy for you to also produce these parts? And that's really what metal 3D printing is creating, is, now that after I'm done, making alterations to my part, I simply upload it to the printer, and in a couple of days, I'm ready to test my part. Similarly with this connecting rod that I have here, we wanted to be able to test, different thicknesses, different geometries to make sure that we're optimizing this part before we actually move to higher volumes. Of course, this is going to be a very, very high loading part inside of an engine. So to be able to actually test some of those geometries in metal is a huge advantage here. So then when we actually move to production, we're ensuring that we have an optimized geometry. Roller screw. This is a part of a linear actuator. It's actually part of a roller screw linear actuator. It's used in a steam power plant to open and close a pilot valve. But here, similar to the roller or to the worm gear, depending on the scenario and what we want to do, you may want to alter the threads. You can see there's a couple different thread options here. And how do we want to do this? And of course, then we're going to want to be able to functionally test this component before we move to a higher volume casting component. So you can see here, a couple different iterations, and then the one that I have with me here today. So this part was actually traditionally manufactured out of 7 different components and then assembled, with some screws, some set screws and some Loctiting components. But now that we're printing the part, it's very possible to simply combine, all those components into one basic part, print it all together, and then we're ready to go. This part can be produced on the studio system for about $86, takes about 4 days. So a huge lead time savings as well as a huge cost savings. And you can see here, that original design was 7 parts with those set screws and those gears that were manufactured separately. And now we can combine it all into one part and print it all together. This heat exchanger, another part that I have with me here today, made out of copper. This is a heat exchanger that's used for cooling fluids in a chemical environment. And you can see the different fins, the different fin patterns that, you may want to iterate on to test how the heat transfer, rate is going to change depending on those geometries, depending on the surface area. It can be very easy to be able to just simply print different, iterations of this and then test them. This part actually features an internal channel that's kind of helicking through the part. The inlet here and the outlet here, it's going to have that channel that's snaking down through the part. And you can see that channel being printed into the part right here. Of course, a feature that's only possible with additive manufacturing because we're able to simply print those features right into the part as we're building it. You can see, it building up, and then the final part that I have with me here today. Golf clubs. Golf clubs have many different variables depending on the type of club you're going to be making, different surface areas, different styles, different geometry, even different bounce angles and different weights and densities and distributions and centers of gravity are all going to want to be factors that you're going to want to try as you're testing these components. So here, there's both the low volume production, if we want to do some customization for, a specific player, specific customer, as well as, before we move to that casting or forging step, we want to be able to try many different golf club variations, rather than having to do this, multi-machining setup, many different machining operations. I can simply, finish my design on my computer this afternoon. I could throw it on the printer and I'm ready to put in the debinder in the morning, allowing me to try many more different iterations to ensure that I'm optimizing the design before I move to those higher volume manufacturing methods. Faucet. I mean, we're keep looking at these design studies, but before we move to higher volumes with faucets again, here we need metal for that user testing. Before we move to those higher volumes, it's not easy to test these components in plastic because they don't have the same feel as a metal component does. So, by printing these different designs in metal, polishing them, now we can actually put them in front of a design study, we can put them in front of a design group, and they can get a better feel of how the part's actually going to look when it comes out to decide which one of these designs do we want to move to higher volume with, how do we want to tweak these designs, allowing for very quick and easy iteration. You can see, one of those polished iterations right here. Pilot run tooling. So, it's quite common, before you move to very high volume to do a pilot run of, maybe a few hundred parts. Oftentimes you're still going to need tooling for those iterations. So for example, this is an asthma inhaler here. The mouthpiece is going to be injection molded. So the tooling here can be printed, the injection molding tooling can be very easily printed on the studio system. You can see, I have 2 iterations here. One of them has that, polished surface. This part was able to be printed to near net shape, reducing 95% of the machining time, and then just the critical dimensions and, the actual molding surface were cleaned up on a mill. This part, it was actually able to incorporate a conformal cooling channel that you can see in that image there. There's 2 different inlets here to allow those different cooling fluids to be flowing through the part and getting very close to the molding surface to ensure that there's optimized cooling. During a molding process, cooling can account for up to 95% of the cycle time. So using an internal cooling channel like this can reduce that by up to 40%, allowing, for a, higher throughput, a higher performance mold tool. These parts are printed in H13 tool steel, an excellent material for, rapidly fluctuating temperatures like you're going to see in an injection mold core that's constantly being heated and cooled. Studio System can produce one of these parts for about $160, so a huge savings compared to having to go to CNC machining, where we're going to be able to just very quickly do a pilot run to test out, a few hundred of these parts before we move to very, very, very high volumes. Zipper molds. So most zippers are actually molded via a zinc die casting operation. This is actually a part by our customer corporation, Ray, and they're constantly getting requests to produce these parts in lower volume. They have customers who want to be able to, market test some of their zippers. They want to place an order of a few hundred, even 1,000 is a small order for zippers, where they just can't justify creating the tooling to produce these parts in such low volume. But now with 3D printing, we can greatly shorten this production lead time. We can rapidly iterate on different zipper designs because we're able to, print the die casting inserts and then actually do some of this market testing. So, each one of these inserts can be produced for just $15. They're then placed in, a multi-unit die, and we're able to actually do some zinc die casting operations to see, different designs of the zippers, how they're performing, and which ones we may want to move to higher volumes with. Extrusion dies. So I have one of these here with me. This is an extrusion die used for in a ceramic battery operation. It's quite a complex shape. I'm actually going to switch to my other camera so you can see it a little bit better. It's quite a complex shape. It's like a perfect lofting scenario for your CAD software, but not a very easy part to manufacture. We're going from that square loft down to that circular loft on the bottom here. I have another one here with me. So again, this part actually just needs to be produced in low volume. We don't need to be making very many of these. So it's a perfect part for us just to simply print rather than having to manufacture, to spend the very, very expensive CNC machining time, or even a DMLS operation was looked at. But, of course, needs to be metal because it's having this, highly abrasive flow going through it. Studio System can produce this part for just $64. Takes about 4 days. CNC machining alternative was about $1,200, taking about 2 weeks. Replacement parts. Another thing that we want to talk a lot about today. This is an example of a thermostat housing. My parts are everywhere here. I do apologize. I have it here. So this is a part that goes onto a vintage Mercedes-Benz engine. You can see the part here. The part was originally cast, followed by some brazing operation to attach the two, the two nose cones. It's a thermostat housing. It's a vintage part. The part, of course, is no longer in production. It's from an engine in the 70s. Replacement parts are quite difficult to come by, if you can come by them at all. Your best chance of finding one of these parts is going to a junkyard and trying to find the same model of the car to pull it out of the engine and put it onto your car. So, printing, replacement parts on the Studio System, generally is a lot more cost effective, especially when they're relatively complex geometries that are not optimized for lower volume manufacturing methods like a machining operation. this part was originally cast, followed by those brazing operations for these 3 pieces. But now we can print it all together as one part, get it onto that, to that engine, and we're ready to go. Gear for earth drilling machine. This is quite a large part I have with me here today. It's from one of our customers, Master Drilling. Master Drilling is a manufacturer of these very large earth drilling machines. They drill miles into the ground, mostly for mining and energy sector. This part is part of a planetary gear set that you can see on screen here, attaches to this large electric motor that then attaches to the actual drill that's doing the drilling, going miles into the ground, mostly for these mining operations. Unfortunately, they had an issue with this large gear. They were originally getting it from a foundry in China with about a 3-month lead time. When one of these gears broke, they needed to replace it as quickly as possible so they could get this machine back up and running, back drilling. Otherwise, they're going to be losing money every day while this drill is down. So moving to the studio system, in just 3 weeks of time, you're able to, print this part, debind this part, sinter this part. They then actually did a case hardening operation to get that hardness value up, and then a machining operation as well for those critical tolerances in just 3 weeks. So from moving from a Chinese foundry down to, the studio system, you can go from 3 months to 3 weeks. It is quite a large part. As you can see here, it's one of the larger parts that we have. But still a huge lead time savings. Hardness coming out of the furnace is about 25 Hardwell Rockwell, and then after the heat treatment process or the plasma nitride, you can get up to 43 or all the way up to 64, which was great. Was the hardness they were looking for this gearing application. One of our customers, Prezioso Francesco, located in Italy, they're using the studio system for many different replacement parts. So founded in 1969, they were a leading vendor of sheet metal cabinets for gas and water meters, on-off valves, heating systems, manifolds, mostly serving the energy, civil plant, and industrial plant sectors. The challenge that they're facing is really this replacement parts for their manufacturing floor. So they're really exploring additive manufacturing for these MRO parts, maintenance, repair, and operations, trying to reduce these lead times, reduce these CNC machining bottlenecks that they're seeing, as well as reduce some of the part mass to lower wear on their components, as well as allow their machines to actually perform to a higher level. One of these parts is this sheet metal clamp for their punching machines. So there's 4 of these clamps per punching machine. The clamp actually allows the sheet of metal to be moved along the workstation. It's typically cut from a hot rolled metal block and then CNC machined with about a 2-week lead time, costing them about $280. So to reduce this, they took their file, they loaded it up onto the studio system, and really saw a lot of different benefits here. So the 4 benefits here was they were actually able to produce a lighter part. They incorporated some infill into the part and got about a 17% mass reduction, which was beneficial for this application just by using some infill. It was faster. They were able to produce the part in 7 days rather than 2+ weeks, about a 36% lower cost, about 176 euros versus 280 euros, and then much less waste, much less material usage relative to their CNC machining alternative. So a great example of a replacement part. Next steps, they're looking to do some more topology optimization. And this is kind of what I was talking about earlier with the justifiable complexity. These features that were added to the part here are actually going to reduce the cost of this part. We're removing material, so we have to use less material. We're also going to reduce the printing time because there's less material to print. We're going to reduce the debinding time because fluid can access the part from more different angles. And that's actually going to reduce the cost of our part. So if we were going to machine this part, we've now added more cuts. We've increased the cost of our part. We now have to remove more material. It may not be justifiable, but since we're printing, we can now add these complex features at no cost to us. Actually so many times reducing the cost. So this is a great example of what I mentioned earlier with this justifiable complex geometry. Another part here is this spring holder hanger. This is part of a paneling machine. This part's coupled with a gear that goes through a spring. It allows this arm to rotate and actually moves the sheet metal panel around in a circle to have this operation perform. Generally, it takes them about 7 days to receive this part if it's in stock, even longer if it requires machining, generally costing about 60 euros. You can kind of see it working here. Down. Rotates the part and then back into the machine. And they also had some issues with actual wear on this component. You can see the tear out here through the holes. They were not getting the performance they wanted. They were finding this part failed quite frequently. So what do? They reverse engineered this component. They added a little bit more strength with the rib components that you're seeing here. Very, very easy CAD project for one of their engineers, probably did it during lunch. They throw it onto the printer and, huge benefits again. Stronger. Now they're able to modify the design to increase the strength. Much faster. In 4 days, they were able to manufacture 6 different samples because they could put multiple of them on the bed, print them all at the same time. They're ready to be mounted in the machine without any post-processing. 75% cheaper. 15 euros versus 60 euros. So huge cost savings. And then again, much less waste, reduced material waste relative to CNC machining. So a great example of using the studio system for replacement parts. One thing I like to mention about this part is most people are not going to buy a studio system just to print spring holders. But once you have this system in-house, so many applications present themselves because it's just so accessible. You know, for example, with this company, you know, they realized that they need to replace this part. And then one engineer said, oh, we have the studio system. I'll design the part real quick and we'll have, you know, 6 samples in 4 days. So it's just something to think about that, you know, just the system is just so accessible. It's so easy to use that you're finding so many applications where it's just so much easier to print the part than to go to some, you know, other manufacturing method or to go to your internal machine shop even, because all I have to do is upload the CAD file and hit print. In a couple of days, I'm ready to install my part onto the machine. So big business impacts for them, you know, ability to print these replacement parts for the manufacturing floor. They're lowering their costs and minimizing CNC machining labor and lead time. They're improving their machine reliability by doing this, you know, this mass productions. Then they're getting this design freedom to increase optimized strength and lower weight when and where they need it. John Zink is also, you know, we talked about them a little bit earlier, but they're also using the system for quite a few replacement parts. They did some work on the USS Blue Ridge. They had a safety device that they installed on there. So, you know, the ship needed some replacements for a yoke and 2 different handles. You know, rather than having to go to a casting supply chain or find a machinist to machine these parts, all they had to do was throw them, you know, take the existing file, upload it to the printer. In a couple of days, they're ready to ship them out. Much simpler logistically than having to go to a traditional manufacturing method where you're going to need a machinist to, you know, much operator burden, you know, maybe some complex programming, maybe some different fixturing setups. Very easy just to simply print these components. YE6 burner tip, you know, this is a component that I have with me here. This is a great story. So this is a part that they originally produced in 1967 for one of their customers. It's another one of those burner components. It has, you know, it's going to be mixing air and fuel, and there's actually a big flame that will be coming out of the bottom of this. The customer asked for a replacement, and they hadn't made this part since 1967. You can see on the drawing on the bottom here, the original date is 1967. It was originally cast. So what they did when they needed to replace this part, they found the print, you know, they found an intern or somebody to CAD it up real quick, and then they threw it on the studio system. And in just, you know, in about a week or so, they're able to, you know, ship this part out the door rather than having to find a new casting supply chain, find a, you know, be very, very difficult, if not impossible part to machine because some of the overhangs on the internals of this part, but, you know, much, much simpler to simply just throw it on the printer, ready to ship it out in a few days. So big business impact for John Zink. You know, low cost metal printing. They're finding lots of applications for that. Taking new designs to market faster. We looked at some of those iterations earlier. You know, avoiding the tooling costs for these low volume parts and getting a much faster turnaround than casting supply chains. Cifarelli, also located in Italy. They are a leading vendor of agriculture and gardening equipment. They have a rich history of technology and product innovation, and they're really looking to incorporate 3D printing across their entire product line. So one part we're gonna be looking at here is this shaker hook. This shaker hook vibrates over 2,000 times per minute and has a stroke of about 62 millimeters. It's used for harvesting nuts and olives. This shaker hook can collect over 3,000 kilograms of olives per day with a falling rate of 95%. So it gets about 95% of the fruit off the tree without damaging the tree or its buds. I don't know about you guys. I don't know how much you like olives, but 3,000 kilograms of olives is a lot of olives. It's a very key component. The design greatly impacts its performance, its reliability, and its usability. So, you know, looking to, you know, the issue with this part was that generally it's being produced in the volumes of a few thousands via aluminum chill casting operation. Of course, aluminum chill casting is not a very friendly, you know, manufacturing method for those low volume applications. So when they do get these low volume requests, you know, for a specific vegetable, specific fruits, for some custom scenarios that a customer needs a specific shaker hook for, they generally cannot economically produce these via casting, so they need to look to a new manufacturing method. So once they look to move to the, you know, the desktop metal studio system, they realize that now they're going to be producing the part in steel since we don't print aluminum, and they realize they need to make some changes to the part to reduce the weight. One thing they did that was very, very smart was they optimized the shaker hook using a generative design software. So by inputting the, you know, original model, applying some loading as well as those frequencies of the shaking, they're now able to come up with a new design that's going to leverage that strength of steel, but is no heavier than the original aluminum component. You can see the finalized part on the right. You can see some of that natural webbing. You know, generally, you know, generative design produces a part that is very, very, you know, optimized for the application, but is not very friendly towards manufacturing. It's very, very difficult, if not impossible, to machine, as well as very, very difficult to cast. Yet these parts are very suitable for an additive method like 3D printing, where we're building the part up layer by layer. You can see, the part ready for printing. You can see the part actually being printed here. And then the final part, it had that, that you cut out, that you added a little bit of stiffness during the sintering process to ensure that it was, ready to go. And you can see the final shaker hooks here. They're ready for field testing. And you can see the part actually being tested here in the field. Awesome. So big business impacts, really allowing them to have this dramatic competitive advantage because now they can offer these low volume customized parts for their customer. They're able to produce these parts that are the same weight, but much stronger because they're able to incorporate, some of this justifiable complexity that I keep talking about, many new applications because they're now able to prototype parts for low cost using metal 3D printing and looking to explore, across their entire product line, as well as move to some higher volumes with the shop system. Turner Motorsports, located here in Massachusetts, they are a leading BMW tuner and race team. One project that they took on was to marry a 2001 BMW M3 with a modern V8 engine. As you can imagine, many of the parts didn't fit together, and what one of those parts was the original engine mount for the 2001 BMW. So what did they do? They scanned the original engine mount, they loaded it into a generative design software. Here it's live parts. You can see these blue different keep out zones. Those are different zones that the software is telling the part, do not come here. If you do, you will interact with the engine. You apply your loading and you allow the part to grow to optimize the design. You can see a couple different iterations of that growth. You can see one of them in the engine here with some Sharpie on it, saying we need to make some changes here. And then you can see the finalized two-part design that you see here. I have one with me here today. This part is actually produced in two parts because it was too large to fit onto the studio system, and then it was simply just welded together. But as you can see on this part, it's featuring those very, very complex natural shapes of generative design that it would really just be a nightmare, if not impossible to machine, but are very, very easy for us just to simply print. Of course, this part's holding the engine to the frame, so steel was a necessity to make sure this part was very, very, very strong. So I've talked a lot about the studio system. I've talked a lot about, some of these lower volume functional prototyping applications, replacement parts, but what about mass production? What about when you need to produce hundreds or thousands of parts, a year or even a week? We have the shop system. And I'll briefly touch on the shop system, but again, if you have more questions, I'm happy to take any questions afterwards, or we have full webinars dedicated to the shop system. But the shop system is really the world's first metal binder jetting system that's designed for machine shops. So what does that mean? It means that you're getting this this accessibility that Desktop Metal has promised. The system is easy to install, it's easy to use, it's coming at a price point that's quite familiar for machine shops. You're getting this unparalleled productivity that you're expecting from binder jetting. We're getting hundreds or thousands of parts per week. And you're getting this very high print quality. You're getting these very high, high quality parts that, people expect to get from their machine shops. So briefly on how the shop system works, the shop system is a binder jetting machine. Binder jetting, as you can imagine, is a process of jetting binder. It is a powder metal process. So on our right, we're gonna have our powder feedstock. That's gonna be our low-cost metal injection molding powder, the same powder that we're using in our studio system, but now rather than it being encased and mixed with the binder, it's gonna be a loose powder. We're gonna spread a layer of that powder across the build box, just about 50 microns thick, and then we'll come across with our print head array and jet binder, onto that layer of powder, but only where our parts are. So here, our jigsaw puzzle pieces are our parts. Our print head would come across and jet binder where our jigsaw puzzle pieces are. We'd then lower the build box by one layer, another layer of powder, and then come again across with the print bar again, depositing that binder to hold the powder together just where our layer of that part is. Since we're printing in this binder jetting method, this print head bar is going to be the entire width of the build box, allowing us to print entire layers in just a few seconds. This allows us to print very, very, very quickly. After printing is complete, we take our parts out of the printer, we depowder them, we place them into the furnace, and we're gonna have a similar sintering process to the studio system, but we don't have a solvent debind here. We can do all of our debinding in the furnace. We're first gonna do a thermal debind where we boil out that last bit of binder, or all of the binder out of the part, I should say. Then we get up to a sintering temperature to sinter into a strong, dense, fully dense metal part, like I have quite a few shop parts with me here today that I'll show you in detail under the scope. So what does this system allow you to do? You're really getting this unparalleled productivity. You know, you're able to produce various different part geometries simultaneously. So if you look at the build volume on the right here, you can imagine asking your machinist to produce you all of those different geometries. You know, think about all the different fixturing that would be involved, all the different machine setups, all the different programming, all the different operator burden that it would take to make all of these different components. You know, that's an example of a 16-liter shop build. You know, I can set up that build in just an hour or two, and I can print it the next day. We're ready to sinter those parts that same week. Much, much, much easier than having your machinist machine you all these different parts. At the same time, if we need many of the same part, I can set up an entire build, you know, with hundreds of the same part and run that overnight. And we're ready to, you know, those parts are coming out of the furnace in just a few days, ready to go, ready to be installed. You know, which makes it great for these mid to low volume applications, especially when the parts are relatively complex and would be quite difficult to machine. So this system allows you to, you know, greatly reduce costs. You know, because of course you're eliminating your tooling. There's no tooling involved. So since we're simply just printing the part, we're reducing lots of tool wear. You know, we're reducing labor costs per part because we can set up this entire build with all these different geometries in just an hour or two. We're greatly reducing our job setup costs because, you know, we don't have to set up all this fixturing as well as all these complex CAM programming. And we're greatly reducing our manufacturing steps as well because we just have to touch up criticals if necessary. Of course, the parts are fully functional out of the furnace. With 3D printing, it's pretty common to talk about reducing costs, but with this system, we're actually seeing a lot of machine shops looking to increase revenue. You know, now we can produce these previously unattainable geometries for our customers. We can print these hard to machine materials like tool steels and super alloys that are, you know, very expensive and very difficult to machine. We can make these small and medium, you know, jobs economically viable. In the past, you know, maybe it was only 10 parts and we had to simply no bid on that order because we couldn't justify, you know, the machinist time as well as the setup time. But now I can simply add that to a batch that's already running and produce those parts in just a few days. You know, this allows us to win new business. Then we also are freeing up lots of CNC capacity in our shop for new jobs because we're simply just printing these large batches of parts. So, you know, binder jetting, you know, we're really able to do this mass production without tooling, which has, you know, many advantages from cost to lead time, as well as just flexibility, where, you know, if I need to make a change to my part, all I have to do is tweak my CAD file, upload it to the printer, and I can have a few hundred in a few days. You can see lots of different geometries here. You know, here's an example of a power drill transmission. You know, of course, you know, your average dual drill or, you know, whatever drill you have, it has this transmission inside. You know, we can produce all of these different gears without the need for tooling. You know, to produce all these different gears via maybe a casting or a powdered metal process would require hundreds of thousands or millions of dollars in tooling. But now we can simply print all these parts simply with no tooling, just a few days. I'm free to modify the design. So depending on the volume I'm producing in, you know, I can really unlock a lower cost. Another part that I have with me here today is the sensor holder. This part is used to hold multiple different sensors in a running machine. These small features on this part make it quite an ideal component for the shop system. You know, printing this part was actually led to an extreme reduction in both manufacturing lead time as well as cost, and as well as, you know, this flexibility that I mentioned. You know, if I need to modify the design to incorporate a different sensor, all I have to do is send a revised file to the printer and I'm ready to go in a few days. So this part can be printed for just $7.80. Can do about 186 of these per build and do about 1,500 of them per week. And that's for that 8-liter shop build. I should mention, shop system comes in a few different sizes, 4-liter, 8-liter, 12-liter, 16-liter, depending on, you know, just how many parts you need to produce. So all of my costing is for the middle one, the 8-liter. You can see it's quite a nice detailed part. Another part, a little bit of a larger part, this bearing housing that I have here. This holds some press fit bearings into a running machine. This part was all about lead time. So they needed this part to be produced quickly, and they needed it out of steel. So using the shop system, they're able to print all of the required parts in just 4 days. They're ready for assembly in less than a week, requiring almost no operator labor. So, this led to a dramatic decrease in manufacturing lead time compared to traditional manufacturing methods. And I actually went on to a common service bureau this morning. I quoted this part, I uploaded my CAD file, and if I wanted to get this part delivered 8/25, so that would be in 12 days, it was going to cost me $197 to get 20 per part to order 20 of these. If I wanted to get them on September 3rd, it was going to cost me $125 per part. Of course, there is some markup with a service bureau, but just to show you, if I need parts quickly and I need to maybe go out of house or I need to hire an external machinist, the costs are so high. But here I could print this part for just $95, and I can do about 175 of these per week with the 8-liter shop system. So a great example of how I can greatly, accelerate that manufacturing lead time. Tons of different parts. I'm not going to talk too much about the shop system today. We have tons of different webinars targeting the shop system. So if you want to learn more about the shop system, I or Dynamism are happy to review more of that with you. But I'm wrapping up for today. I really thank you for joining me. I appreciate you taking time out of your day. I hope everyone is staying safe out there. I'd love to explore, with Dynamism and I, what metal 3D printing could do for your business. So what does that mean? I'd love to schedule a meeting with you. We'll be sending around a link afterwards with the recording and the slides, an opportunity to set up one of these meetings. And really what this meeting is just an opportunity to talk a little bit about, your manufacturing environment, the parts you're creating, and to see if a metal 3D printing system could be a good fit for you, if it's going to add value. We're also happy to provide free part assessments. If you want to email me a CAD file, I'm happy to look at the part, let you know if I think it'd be a good part for printing, as well as what it would cost and what the throughput would be on any of our different machines, to give you a better idea of how these machines are adding value and what kind of parts are good for this machine. And of course, if things are looking good, we're happy to provide free part samples to help you with your buying decision. Great resource. I really encourage you to sign up for one of these meetings. Just an opportunity to really understand a little bit better about how 3D printing can add value to your business. Thanks again. Feel free to reach out to any of us via email, either Eric or I at Dynamism. We're happy to answer any other questions. We'll be, of course, distributing slides and a recording after this. Really appreciate, everyone taking time out of their day to learn a little bit more about desktop metal, about functional prototyping, low volume production. We'll stick around, of course, to answer some questions at the end here. If you want to keep chatting in questions or have any thoughts or comments or want me to explain anything again, I'm happy to stick around. Thanks so much for joining me, everyone. I really appreciate it.